Module 4, Section 9.3, Further Identities. The double number identities result from the sum identities. When we let a equal b, then we add a plus b, we're really adding a plus a, and we get 2a. Recall one of our sum identities here. When we replace b with a, we have the cosine of a plus a, which results in the cosine of 2a, and we see that we end up with cosine squared of a minus sine squared of a when we work it out. This is one of our identities for our double numbers. Now let's also recall our Pythagorean identity, sine squared of a plus cosine of squared of a equals 1. If we solve this for cosine squared of a, we get 1 minus sine squared. So in the identity that we just found, if we substitute 1 minus sine squared of a in where cosine squared is, we have the following, and when we evaluate it out, we get 1 minus 2 sine squared of a is another double number identity for cosine of 2a. And then if we also solve our Pythagorean identity for sine squared, we get 1 minus cosine squared, which we'll substitute back into our original here where we had sine squared of a, like so. But notice when we subtract our expression here, we change the sign of both terms, so we're subtracting 1 and then adding cosine squared. So we end up with 2 cosine squared of a minus 1. Here we have listed all of our double number identities. You see the 3 that we found for cosine of 2a, plus the ones for sine of 2a and tangent of 2a. Let's verify an identity using these double number identities. What we'll do is we'll work with our left-hand side. So we'll change cotangent into sines and cosines. It's the cosine of x over the sine of x. And we're multiplying that by the sine of 2x. Now the sine of 2x, we see from up here, is simply 2 sine of x cosine of x. And we'll put that over 1 to make it a fraction, and we can cancel our sine of x, and we end up with 2 cosine squared of x. Now also notice up here we have the cosine of 2a, or 2x in this case, equals 2 cosine squared of x minus 1. If we add 1 to both sides of that identity, we have 1 plus the cosine of 2x equals 2 cosine squared of x. So here we found that when we worked out the left-hand side, we got 2 cosine squared of x, which is equal to 1 plus cosine of 2x, using our identity. So we've proven that our equation is an identity. In this example, we are given the cosine of theta as 3/5 and told that sine of theta is less than 0 or that it's negative. And we want to find the sine of 2 theta, the cosine of 2 theta, and the tangent of 2 theta. So first we need to find a value for sine. So we'll use our Pythagorean identity that sine squared plus cosine squared is equal to 1. And we'll plug in the value we have for cosine as 3/5, and we want to square that. When we square it, we'll get 9/25. We want to subtract that from both sides. So we have that the sine squared of theta is equal to 16/25. We want to take the square root of both sides. Now normally when we take the square root, we get sine of theta equals plus or minus the square root of 16/25, which is 4/5. But we're told here that the sine of theta is negative, so we know we just have our negative answer here. So now that we've found our sine value, let's find the sine of 2 theta using our double number identity. We have that it's 2 sine of theta cosine of theta. So it's 2 times negative 4/5 times 3/5. And when we work this out, we see that we get a value of negative 24/25. Now let's find the cosine of 2 theta. It's equal, we'll use the first one, we had 3 to choose from, the cosine squared of theta minus the sine squared of theta. So we have 3/5 squared minus negative 4/5 squared, or 9/25 minus 16/25. So we end up with negative 7/25. Now to find the tangent of 2 theta, we can use the identity that we found, which was, or that we were given, which is 2 tangent of theta over 1 minus the tangent squared of theta. But to use that, we would need to find the tangent of theta using the fact that it's the sine of theta over cosine of theta. There is another possibility. Since we found the sine and cosine of 2 theta, we can just leave tangent of 2 theta as sine 2 theta over cosine 2 theta. So we have negative 24/25 divided by negative 7/25, which means basically we're multiplying by 25 over negative 7. So we end up with positive 24/7. Let's look at simplifying expressions using our double number identities. Here we're going to use the identity, the cosine of 2a equals cosine squared of a minus sine squared of a. So we see here that a is 7x. So our expression becomes the cosine of 2 times 7x, which is equal to the cosine of 14x. Now this expression in part B, sine 15 degrees, cosine 15 degrees, is almost our sine of 2 theta, or sine of 2a, which was 2 sine a cosine a. What we're missing is the multiplication by 2. So we're going to change this and we're going to multiply it by 2. But we can't just arbitrarily multiply by 2, so to make it multiplication by 1, which is allowed, we'll also multiply by 1 over 2. So we end up with then 1/2 times the sine of 2 times 15 degrees, since we see that a in this case is 15 degrees. So we then have 1/2 the sine of 30 degrees, and we know that the sine of 30 degrees, if you evaluate that, is 1/2. So we have 1/2 times itself, or 1/4, as our value here. Now let's look at some more identities. Here we have the product to sum identities. Now bear in mind you don't need to memorize these, so the biggest thing is you need to know how to apply them and use them in problems. So we want to do an example. We'll rewrite the cosine of 2 theta, sine of theta, as the sum or difference of two functions. So here we'll use cosine sine, and we see that a is 2 theta and b is theta. So we're going to use here, we're going to replace a and b with the values we just found, and we end up with 1/2 times sine of 2 theta plus theta minus sine of 2 theta minus theta. So that will be 1/2 times the sine of 3 theta minus the sine of theta. So all I'm going to do here is distribute my 1/2, and I get 1/2 sine of 3 theta minus 1/2 sine of theta. And that's how they want us to rewrite it. Here we have our sum to product identities. Again, you don't need to memorize these, but we need to apply them. So in this example, we want to write sine of 2 theta minus sine of 4 theta as a product of two functions. So in this case, we're using sine minus sine here. And we have that a is 2 theta and b is 4 theta. So we rewrite it as 2 cosine of a plus b, or 2 theta plus 4 theta, over 2 times the sine of a minus b, or 2 theta minus 4 theta, over 2. And we see that that's equal to 2 times the cosine of 6 theta over 2 sine of negative 2 theta over 2. So we have 2 cosine of 3 theta times the sine of negative theta. Now remember that the sine of negative theta is equal to negative sine of theta. So we can change this to get negative 2 cosine of 3 theta sine of theta. Here we have our half number identities. Notice that we have 3 different identities for the tangent of our half angle, or a over 2. So let's do an example. We want to find the exact value of cosine of pi over 12. Now pi over 12 will be in quadrant 1, so the cosine of pi over 12 is positive. So when we're using our identity for cosine of half angle, we'll use the positive here. Now pi over 12 is equal to pi over 6 divided by 2. So we have that a is pi over 6 in this case. So we'll use our identity here, and we end up with the square root of 1 plus the cosine of pi over 6 divided by 2. Now the cosine of pi over 6, when we use our triangles, pi over 6, remember, is 30 degrees. So across from that is 1/2, square root of 3 over 2, and 1. The cosine will be our x value, or the adjacent over the hypotenuse. So we end up with 1 plus the square root of 3 over 2 divided by 2. Now when we add in the top, we take this and we change 1 to 2 over 2, so when we add that up we get 2 plus the square root of 3 over 2 in our numerator. And instead of dividing by 2, we can multiply by 1/2, so we end up with the square root of 2 plus the square root of 3 over 4. Split that up and take the square root of the top over the square root of the bottom, and the square root of 4 is simply 2. In this example, we want to find the exact value of the sine of 67.5 degrees. Notice that 67.5 degrees is equal to 135 degrees over 2. Now when we take the sine of a over 2, it's equal to plus or minus the square root of 1 minus cosine of a over 2. But the sine of 67.5 degrees will be positive since it's in quadrant 1, so we're going to use the plus of this identity. So we have that the sine of 67.5 degrees is equal to the sine of 135 degrees over 2, which is equal to the positive square root of 1 minus the cosine of 135 degrees divided by 2. Now let's look at our triangles here. 135 degrees will land us in quadrant 2, and when we find the reference angle, we take 180 minus 135 and we get an angle of 45 degrees. So we know with our right triangle here we have the square root of 2 over 2, square root of 2 over 2, and 1. And in this case, we're in the negative side for our x value, so we have negative square root of 2 over 2 down here. So when I want to find the cosine of 135 degrees, it's going to be my x value, or my adjacent over my hypotenuse. So we have negative square root of 2 over 2 divided by 2. So that's going to be equal to the square root of 1 plus the square root of 2 over 2 divided by 2. And we'll change this to 2 over 2. So I have the square root of 2 plus the square root of 2 over 2, all divided by 2. Lots of 2's. So here we then have the square root of 2 plus square root of 2 divided by 2 multiplied by 1/2, which will be the square root of 2 plus square root 2 over 4. And we'll split it up, and it'll be the square root of 2 plus the square root of 2 divided by 2. Let's look at finding function values of x over 2. Given that the cosine of x is 2/3, with x lying between 3 pi over 2 and 2 pi, we want to find the cosine of x over 2, the sine of x over 2, and the tangent of x over 2. First, let's look at our interval here for x. We are wanting to find x over 2, so we need to divide each of these by 2, which means here we'll multiply by 1/2. So we end up with an interval of x over 2 being between 3 pi over 4 and pi. So this puts x over 2 in quadrant 2. In quadrant 2, the sine is positive, the cosine is negative, and the tangent is negative. So when we're finding these, we're going to use the positive for sine and the negative for our other two. So let's look at the cosine of x over 2. Our identity says it's equal to the square root, in this case we'll use negative, of 1 plus the cosine of x over 2. So we have negative square root of 1 plus 2/3 over 2, which is equal to the negative square root of 5/3 times 1/2, which will be negative square root of 5/6, which when we work that out we'll get negative square root of 5 over square root of 6. We'll rationalize that denominator, so we'll end up with negative square root of 30 over 6. Now let's look at the sine of x over 2. Sine is positive, and we have the square root of 1 minus the cosine of x over 2. So we have positive square root of 1 minus 2/3 over 2. So that is going to be equal to the square root of 1/3 times 1/2, which is the square root of 1/6. So we have the positive 1 over square root of 6, and we'll rationalize that, and we end up with positive square root of 6 over 6. Now to find the tangent of x over 2, I'm simply going to use sine of x over 2 divided by the cosine of x over 2. So we'll use our previous values, and we have square root of 6 over 6 divided by negative square root of 30 over 6, or multiplied by 6 over negative square root of 30. So we'll have the square root of 6 over negative square root of 30, which is equal to negative square root of 6 over 30, since we can put it back together. That'll reduce down to negative square root of 1/5, which is negative 1 over the square root of 5, and we'll rationalize that. So we end up with negative square root of 5 over 5. In this example, we want to simplify the following expression. Notice it matches up with our identity for cosine of a over 2, which was plus or minus the square root of 1 plus cosine of a over 2. So in this case, a is equal to 12x, So we have the cosine of 12x over 2 or the cosine of 6x.